Okay, we are continuing now with the discussion of electrostatics. We said that electro relates to electricity, and electricity is basically the presence, or used typically the motion of charges, right? Positive charge, negative charge. As it moves, you get electricity. And static refers to static, which is the opposite of dynamic, which means the object is stationary rather than moving. So if you have a charge that's stationary, then you have electrostatics. If you have a charge that's moving, it's electrodynamics. So we move on now to this slide. Let's look at the previous slide. We talked about electric fields in the last lecture, which was 2 days ago, and how you could plot an electric field. And we also talked about lines of field lines. So here's an electric field line traversing from a positive charge along this curve to the negative charge. And we said that the field line is the trajectory of a charged particle. If you place a positive charge, okay, you've got a fixed positive charge and a fixed negative charge here. Now you have a free positive charge that you place here. That charge would move along this trajectory from repelled by the positive charge and attracted by the negative charge. Follow this trajectory until it bumps into the negative charge there, right? So that was electric fields. We move on now to speak of electric potential energy. Now, there is an analogy with gravitational potential energy, right? So let's say there's an anvil, here's a string, there's a pulley over there, and the string is taut holding up this anvil. This anvil is above the ground, so by virtue of being above the ground, it's in the presence of a gravitational field. The earth is pulling down on this anvil, so this gives the anvil potential energy. The energy to potentially do something. It has a potential to do something. Now, what happens if we cut the string? You cut the string, what happens is the earth, the weight of this object, the earth is pulling the object down, the object accelerates, its potential energy gets converted into kinetic energy, energy of motion, so the object has a lot of kinetic energy here, and the kinetic energy is then used to crush this metal can, right? So potential energy gets converted into kinetic energy. This is gravitationally speaking. In the presence of a gravitational field, the object has a potential energy by virtue of its position. Similarly, in an electric field, so I'm creating an electric field by placing a negative charge here. Now I have the same situation where I have the string, pulley, and I have a positive charge applied here, right? Let's say there's no gravity. We've eliminated gravity. So the only force here is an electric force, the force of attraction between this negative and the positive, right? So here's a positive charge, negative charge. There's a force that's pulling it towards this. The string is holding the charge back by virtue of the position of this charge in the electric field that's due to the negative charge. By virtue of the position of the positive charge has potential energy. In this case, the potential energy is electric potential energy, not gravitational potential energy. Is this clear?
Well, so really the only big difference between the gravitational potential energy and the electric potential energy is that one would be an electric field instead of a gravitational field.
Correct.
Okay.
Yes. You can have different kinds of field, and those have potential energy of different kinds, right?
And then depending on what that type of field is, that would be whatever type of field it is, potential energy.
Yes.
All right.
So you have extra credit for the question. So this would give us electric potential energy. You could have a quote-unquote magnetic charge, I'm saying this colloquially, in the presence of a magnetic field, and now you have magnetic potential energy. Wherever you have a force, you can have a potential energy associated with the force, like gravitational force, gravitational potential energy, electric force, electric potential energy. The weak nuclear force can in principle give you a weak nuclear potential energy. The strong nuclear force can in principle give you a strong nuclear potential energy, and so forth, right? Yes, good question. Extra credit to you and to you. So in this situation, I said that we switched off gravity with that little switch that I have down there, right? But let's say I did not switch it off, and let's say this has a certain mass. This mass is attracted towards the earth. So there will be gravitational potential energy plus the electric potential energy. Both of these result in forces pulling the object down, right? Now, it doesn't have to be that these forces are pulling in the same direction. If I reverse this charge, if I make this positive and that's positive, electric potential energy is pushing upwards, right? The electric force is, so gravity is pulling this downwards, electric force is pushing upwards, so the two can cancel each other. And this is how you can get levitation, right? So have you ever seen anyone levitating?
David Blaine.
Oh really?
And
What is he, a magician? Okay. I'm kidding about that kind of levitation, but you know, magnetic field levitation, right?
There's a
Like an electric train?
that you can do by putting essentially nickel washers,
Okay.
and then putting a type of putting an electromagnet on your shoes, and then an electromagnetic plate on the ground, turning it on, and then you can essentially float above that plate.
Extra credit to you if you can send me a link to a YouTube video of that, right? In principle, that's possible. I have never seen anyone have fields that are strong enough to do that, but I would love to see a video. It would be a neat demo for the class too, right? Okay.
There's a magazine that you get on airplanes where you can buy stuff.
Sky Mall.
They have a levitational bed in there.
Oh, really?
They put an electromagnet on the ground and big magnets on the bottom of just a mattress.
Okay.
So it's supposed to be floating around here, I think.
Pretty neat. Extra credit to you. Mademoiselle?
There's quantum locking, does that count?
There's what?
Quantum locking, does that count?
What on walking?
Quantum locking?
Tell me more.
They took some super cool materials and I can't remember exactly what they did. I can.
So the object levitates above the superconductor,
Yeah.
right? Yes, good point. Extra credit to you. Yeah, again, that's the same. In the case of superconductive levitation, what's basically happening is you typically have a magnet or something of the sort, or you're depending on a current in a metal piece. And what happens is that creates a magnetic field that opposes. The superconductor is very good at rejecting magnetic fields, and so what happens is it's just as if you place another magnet beneath it, and that magnetic field force is exactly compensating for the gravitational field force, right? But good point. Extra credit to each of you who's spoken up. Excellent. Right? Did you speak up?
I sure did.
Okay, then you got your extra credit.
Wrote it down.
Perfect. Okay, so that's the case here. So electric potential energy is the energy a charged object possesses by virtue of its position in an electric field, right? So electric field is due to this charge. That charge is being placed in this charge's electric field, and so it experiences a potential energy. Okay, next slide. The previous slide talked about electric potential energy. Now we move to electric potential. Electric potential is equal to the potential energy per unit charge. So take the electric potential energy divided by the charge, the number of Q, the number of coulombs, and you get the electric potential. So electric potential is the electrical potential energy divided by the charge. The units would be 1 volt for electric potential is 1 joule, which is potential energy divided by the charge, which is in coulombs. So illustrating the difference between the two of these, if you had a metal sphere on an insulating base, and the metal sphere has a bunch of positive charges, and let's say that you were to take two different little objects and touch it to this to get a certain amount of charge on this. So A is a little object with a bunch of charge, B is a bigger object with more charge. You could have a situation where the potential, that is the potential of each of these, the electrical potential is equal to the potential energy divided by the number of charges. So you can charge them to the same potential, which is energy per charge, while having a different potential energy. So at the top, potential energy of B is greater than the potential energy of A because there are more charges in B. However, that's the potential energy. The potential, which is the potential energy per unit charge, is the same for the two of these, right? So the illustration of this in practice would be the 6 of you, 6 of you, 6 of you. Okay. How about this? If I were to put all of the students here in one of those spheres and the rest of the students in another one of the spheres, let's say that I have to give each of you $10. Your potential is $10, right? Each of you has the same number of dollars. However, the potential energy of this whole sphere is twice the potential energy of the sphere, because there's twice as many students here as there are here. Make sense? So total potential energy is the $10 plus 10 plus 10 or whatever. So $60 here. Over here, it's $120. Yes? That's the potential energy, adding up all the dollars of all the different students. But the potential is the potential energy per student, $10. The $10 is a potential energy. Because remember what money is. In principle, in a stable economy, money is a representation of labor. If you say that you get paid $15 an hour for whatever job, right? If you get paid $15 an hour, if you have $15 in your wallet, it is a representation of your 1 hour of labor. So you could hire somebody else. You could hire him for $15 to do 1 hour's worth of labor. This is presuming that labor is the same cost everywhere, irrespective of your leverage, right? So in a regular, if you have $150 that you have saved through your industry, through doing things, you have saved 10 hours worth of labor. With someday in the future, you can trade off with somebody else. You can have somebody else do 10 hours of labor for you. That's what money really is. It's a representation. Just like this, potential, if you will. So you can think of money as potential energy for you. You have the potential to move the economy in your direction. You have the potential to move a laborer of some kind in your direction. That's what money is.
Wait.
Same thing with potential.
So the $10 per person is the potential energy, the 10.
It's the potential.
Potential energy.
Potential.
Just the potential.
Yeah, it's a
And
potential
then-
because it's divided by number of
And then
students.
all of the, okay, but then the money that all the student has combined is the potential energy.
Right.
Got it.
So if you think of the total potential energy, the 12 students here can accomplish much more than just those 6 students. So as a whole, you can accomplish much more. But as an individual, you can accomplish exactly the same amount that he can or she can. Right? So that's an illustration to help you to understand the difference between potential energy versus potential. Okay, so here, another illustration, potential energy versus potential. You have a balloon. Balloon gets charged up to 5,000. You remember we talked about taking a balloon and rubbing it on somebody's hair, like at a party or whatever? It can get charged up to 5,000 volts. This is why you're going to put your finger on it. Sometimes you'll get an electric spark, right? Electric spark can be anywhere from 5,000 to 20,000 volts. In the semiconductor industry, we assume that human sparks can range from 5,000 to 20,000 volts. This is why it's so easy for you to kill a computer. You open it up, right? Stick your finger on the microprocessor without appropriate safeguards, and there's a little spark, and you just died. I mean, you killed a $500 chip or a $1,000 chip or whatever, because the spark that jumps from you to the chip can be 20,000 volts. So in this case, it's 5,000 volts, but you don't get severely hurt, right? And the reason is because even though the potential is 5,000 volts, the potential energy is small because the amount of charge is very small. On the other hand, you can get killed by sticking your finger in one of these little socket thingies, right? It's 110 volts, which is much less than this. The energy here is much less than here. The potential is less. However, the total potential energy is much greater because it's pretty close to an infinite supply of electrons here. Whereas here, it's a very limited supply. It's like being eaten by one ant versus one of those things in some places, the Amazon or wherever, or Africa, where you have these soldier ants or whatever. I forget what they're called. They march in columns and they eat everything on its way. So you better get out of the way or you get totally eaten, right? And there's nothing left of you but a skeleton. So it's kind of like that. So in this case, you have an infinite number of ants coming to eat you. In this case, you just have 4 ants. Yeah, it might hurt if they bite you, but that's about it, right? So again, another illustration of electrical potential versus potential energy. So electric potential energy per unit of charge, right? Potential energy divided by the charge gives you the electric potential. Voltage is the electrical potential energy divided by the amount of charge. So when you say that there's 110 or 120 volts of potential coming from one of these plug points, that's telling you that that is the potential energy per unit charge, per Coulomb of charge coming from the wall. Next slide. Introducing the concept of a capacitor. A capacitor is a device that has the capacity to store charge, hence the name. It's basically typically just two metal plates that are close to each other. You connect them to a battery, and what happens is positive charge comes and lands up here, negative charge comes and lands up here, right? Or alternatively, electrons come and land up here, and you're sucking electrons out of here, right? So you end up with a positive charge here, negative charge here, and as long as these two plates don't short out, as long as they don't connect to each other directly here, you store the charge. The amount of charge is equal to Q, which stands for charge, is equal to C, which is the capacitance of the capacitor, multiplied by the voltage. So if I apply 10 volts between these two plates, I can store a certain amount of charge. If I apply 100 volts, I store 10 times that amount of charge, which is literally means 10 times the number of electrons get stored. Now the capacitor gets charged up, and then you disconnect this, the capacitor stays charged. Now this is the reason why you don't want to go and like open up your TV or your computer and start sticking your finger at random spots. because particularly in a TV or in a refrigerator and stuff like that, or with motors, you've got these capacitors that are charged up to pretty high voltages. So you disconnect it from the mains, you go and stick your finger in and you get shocked or killed, right? Because what happens is the capacitor discharges, sends out all the charge through you, even though it's not connected to the mains, because it has been storing the charge. Okay, so reminder for you to go over the multiple choice questions.